Hey everyone, today we're embarking on a pretty fascinating anatomical journey into the beating heart of some seriously heavy machinery. We're going to examine the complex hydraulic system of a MacGregor crane. And as we go through this explainer, I want you to try and think of this equipment not just as, a static piece of metal, but almost like a living, breathing mechanical organism. We're going to break down all that dense engineering behind how it moves, how it lifts, and how it protects itself into clear, easy-to-digest pieces.
Okay, let's dive right into our structural blueprint for today. We'll be looking at four main areas. First, the hydraulic power unit. Second, the main motor and pump. Third, the emergency power unit. And finally, circulation and maintenance.
So, this text is straight from our source material for today, the actual MacGregor user manual. Now, I know that looking at dense technical text like this can feel a bit overwhelming right off the bat, but hey, that's exactly why we're here. We're going to decode this manual step by step. By the end of this explainer, you're going to understand the mechanical anatomy described here perfectly, and we'll use these step-by-step visuals to make it all click.
All right, Section 1, the hydraulic power unit, the central core.
So, first things first, where does everything actually live? Well, the HPU, or hydraulic power unit, is the central core of the whole system. According to the manual, it's tucked safely away inside what's called the rotating crane king. I kind of like to think of the crane king as the protective ribcage of the machine. This heavily armored central location is absolutely vital because it houses all the critical internal organs we're about to explore. It keeps them completely safe from that harsh, salty maritime environment while the crane goes about its heavy lifting.
Moving on to Section 2, main motor and pump, the mechanical muscles.
Now let's actually visualize how these muscles are built. Notice the precise vertical stacking order to this main assembly. Starting right from the bottom, bolted underneath a thick plate, we have the electric motor. Above that sits the adapter flange, followed by a flexible coupling, and finally, mounted on the very top, is the axial piston pump. And here's a really amazing detail. There isn't just one of these stacks. There are four main motor and pump assemblies in total. That's 3 single pumps and 1 double pump, all working together in unison.
And, this setup brilliantly illustrates a crucial engineering challenge. Take a look at that flexible rubber coupling mentioned right in the middle of the stack. Why on earth do we need rubber sandwiched in the middle of all this heavy-duty steel? Well, the electric motor spins at a constant speed to drive the pump, right? And that generates massive shaking forces, which engineers call torsional vibrations. On top of that, the connecting shafts might experience slight axial, radial, or angular misalignments. Without these flexible rubber joints acting as heavy-duty shock absorbers, all that violent, chaotic energy would literally tear the machine apart. It is quite literally the cartilage saving the joints of our crane.
And honestly, it absolutely needs that level of protection because of the sheer, raw power involved here. These axial piston pumps generate a staggering maximum operating pressure of 320 bars. Just to put that into perspective for a second, a typical car tire is inflated to about 2 or 3 bars. So we're talking about internal pressures over 100 times greater contained within these hydraulic lines, all to lift multi-ton loads into the air. It's wild.
So the real question is how the crane actually manages all that immense power without breaking a sweat. The manual introduces a pretty heavy piece of jargon here, variable displacement. Let's just break that down simply. While the electric motor spins at a constant speed, the crane obviously doesn't always need to move at maximum speed, right? It needs finesse. It achieves this by adjusting the angle of something called a swash plate inside the pump. By tilting this plate, the pump infinitely varies the actual volume or displacement of fluid it pushes out. Think of it like a volume knob for hydraulic power. This means whether the crane is hoisting a load up and down, slewing side to side, or adjusting the jibs, the fluid flow automatically adapts to keep the pressure drop perfectly constant across the control valves. It's an incredibly smart, dynamic system.
Section 3, the emergency power unit, the built-in fail-safe.
Look, you never want to be lifting tons of cargo over a ship's deck without a solid backup plan. You just don't. Because of this, the crane is fitted with a completely separate emergency power unit, which is also safely hidden away inside the Crane King. It consists of its own variable pump, a bell housing, another flexible coupling for that crucial vibration control, and a dedicated electric motor. Now, unlike the primary system we just talked about, this emergency pump is load sense regulated. That basically just means it strictly reacts and provides power only based on the immediate demand of the load if the main system goes down. And since this is literally your last line of defense, it has to be absolutely bulletproof. The manual specifically notes that the emergency variable pump is fiercely protected by a dedicated safety relief valve. This is an absolute necessity. If things go critically wrong and you have to rely on this backup, this relief valve guarantees that the emergency system itself won't overpressurize and burst under the sudden strain. It ensures your safety net doesn't snap right when you fall into it.
Finally, Section 4, Circulation and Maintenance, the machine's caretaker.
Now, what's really interesting here is the stark contrast between the two types of pumps we've discussed today. On one hand, our main pump uses variable displacement, meaning its fluid flow is constantly fluctuating up and down depending on what the operator is doing. But on the other hand, the circulation pump uses fixed displacement. Because the electric motor driving it runs at a constant speed and the two-screw pump inside has a fixed volume, the flow of oil remains strictly, unwaveringly constant. It never changes its pace no matter what the crane is doing. So why does it need that constant, steady flow? Well, because of its continuous vital duties. This circulation pump assembly acts exactly like the crane's kidneys. Its entire job is to constantly push oil into the main return system. But before that oil gets back to the reservoir, it gets forced through two very well-dimensioned return filters to scrub out any microscopic metal shavings or contamination. Plus, it regulates the overall temperature by pushing the fluid through oil coolers. Because this system relies on that fixed displacement pump, we're guaranteed a constant rate of filtration and a safe oil temperature, entirely independently of how hard the crane operator is working the machine.
When you really look closely at the source material, you realize that a massive crane isn't just about raw brute strength. It's actually about elegant, intricate engineering. It's the brilliant interplay of flexible rubber couplings absorbing those violent physical shocks, dedicated relief valves standing guard over fail-safe systems, and a tireless, independent circulation system constantly cleaning and cooling the literal lifeblood of the machine. It is a true symphony of mechanical anatomy designed to prevent catastrophic failure, even at 320 bars of pressure. So the next time you see one of these metal giants out in the wild, ask yourself, how does your equipment handle the pressure?